Okay. Our first speaker this morning is Professor Thomas Hanne. Thomas Hanne is a professor at the University of Applied Sciences and Arts in Switzerland. He received a master's degree in economics from Ruhr University, Bochum, a master's degree in computer science from University of Dortmund, and a PhD in economics from Bern University, Hagen. From 1999 to 2007, he worked at the Fraunhofer Institute of Industrial Mathematics in the Department of Optimization as senior scientist. Since then, he is professor for information systems at the University of Applied Sciences, Northwestern Switzerland. Thomas Hanne is author of about 50 journal and conference articles. His current research interests include multi-criteria decision analysis, evolutionary algorithms, meta-heuristics, scheduling, discrete event simulation, logistics, and supply chain management. Please welcome Professor Thomas Hanne.
Thanks a lot, Mr. Chairman. Good morning, ladies and gentlemen. You see the topic of my talk. It sounds a bit complicated, multi-objective, multidisciplinary decision-making. First, I would like to ask you, who of you has heard about multi-objective optimization or multi-criteria decision-making? Something? Okay. Not so many? Okay, 2, 3 or so. So my talk will not be very technical. I will try to give you an overview of what the basic ideas of multi-criteria decision-making are and how this discipline has developed over time, and also where the people come from different disciplines, from different nations. It's quite international discipline, and this I would like to motivate a little bit. Okay, let's start with a look at the content. So first I will say a little bit about what we understand by a multi-objective or a multi-criteria problem. Then I will briefly introduce the notion of Pareto optimality, which is very central to the whole research field. Then I will give you a very, very brief overview of methods which we find in multi-criteria decision-making. After that, I will discuss the roots. Where does this discipline come from and how did it develop during the last decades? And then I will show you a little bit of data about the internationality and the different disciplines where the researchers in that area come from. And finally, I will conclude with an outlook to current and future possible trends. Okay, so let's start with multi-objective problems. So multi-objective means we want to optimize or we want to consider several objectives at the same time. This is something what happens very, very frequently. I've got here a famous citation from one of the books in that field. Multiple criteria are all around us. Here you can see a list of some examples where we find such problems in business, in industry, but also in our private lives. Just have a look at that. Very often, for instance, we consider cost as one criterion and quality aspect as another criterion. For instance, when we buy consumer products. So usually there's not just one single thing to consider, but different aspects or criteria to be taken into consideration. This is the most complicated slide I will show you. The only mathematical formula, just to give you an idea how this is treated from a mathematical point of view. So when we formulate a problem like that in a mathematical way, we can describe it as a function f, which maps some kind of alternative or solution, which can be described as an n-dimensional vector, to another q-dimensional vector, where each of the components of the vectors make up the different criteria or objectives to be considered. So this is a very broad and general description of such kind of a problem. So we do have basically two q objectives. And another question is, what kind of variables do we consider in problems like that? So for instance, the variables, they could be real valued. They could come from a discrete domain like integer values or binary values. And usually, of course, we also want to consider some kind of restrictions. So not any kind of of alternative or variable is feasible, but only those which fulfill particular constraints or restrictions. Okay, so this is a very complicated formulation. I will show you a much more simple type of multi-criteria problem where we do have a finite set of alternatives. So let's assume we do just have m alternatives, which we consider and which are explicitly given. Then we don't need to consider objective functions, which can be more or less complicated from a mathematical point of view, but we can directly write down the different criteria values of each alternatives, and then we've got a table with m alternatives and q criteria. So that looks very simple, and I will show you an example how a problem like that could look like. So let's assume we want to buy a new portable computer. And moreover, let's assume only 4 criteria are relevant for us, which could be, for instance, the speed of the CPU, the memory, and the display size. All those should be maximized. Now, let's assume this is the situation. It could be, of course, differently, that we want a very small device, for instance. And moreover, we consider the price, which should be as small as possible. Then we could make a market analysis, find out some data from dealers, and write everything down, and then we would get a table like that. And then, of course, the question would be, which one should we choose if we only look at those data? For instance, if we only consider the price, then this is something very cheap. The price is given here in Swiss francs. If we look at the speed of the CPU, then this one and this one would be the best. If we look at the display size, this one would be the best, and this one as well. So different alternatives are better considering the different criteria. If we look for a good compromise, maybe the second or the third are quite good. They are not too expensive, and the power is also quite good, also the display size. So not so easy to say which one could be the best. But if we look at some alternatives, we could say something quite clearly. So for instance, when we compare alternative 2 and alternative 5, this one, we would see this one is faster. It's got the same memory. The display is larger, and it's even cheaper. So we could say this is clearly better if we only look at those data. And we could find a similar result when we look at this one. If we compare the tools, we could also say this is faster, RAM is the same, display size is larger here for this one, and it's cheaper. So for some combinations, we could say one is clearly better than the other ones, and this is called Pareto optimality. So we say one alternative is dominated or inferior if there is another alternative which is better in at least one of the objectives and not worse in the other ones. Then it's clearly better. And so we call all those alternatives where we do not find another alternative which is clearly better, so better in one aspect and not worse in the others, non-dominated or Pareto optimal or efficient. Unfortunately, if we look here at this example, here, if this is the set of alternatives, we do have 2 objective functions. We want to minimize them. Then here along this curve, there are the Pareto optimal alternatives. So quite many here, 5 examples, A, B, C, D, and E are denoted. And we see F and G would be dominated because, for instance, C is better with respect to both criteria than G. But among those, we cannot find an alternative which is clearly better. Here we can clearly say it depends on what we want to do, which one we should finally choose. If this objective is very important, then A and B could be very good solutions. If this objective is the most important, then maybe D or E are the best solutions. If we want to find a balanced compromise, then maybe C is the best one. So that means from a purely mathematical point of view, we cannot say which of the Pareto optimal solutions is the best ones. So we need to do something more. And what is usually done is that we need to consider what a decision maker really wants, what the preferences of a decision maker are to finally come to a conclusion which of the solutions should be selected. And for somehow taking information from a decision maker into account, a lot of methods have been developed during the last 40 years, and this discipline is called multiple criteria decision making. I would like to give you a very brief overview of some of the methods or basic ideas which are considered when people deal with multi-criteria problems. I would like to look at this list of methods just very briefly to give you a very rough idea of what the ideas behind the respective methods could be. Let's start with something very, very simple. Simple additive weighting, or sometimes also called scoring. This is a very intuitive idea. When people do not know anything about MCDM and they are faced with different criteria, what they usually do is try to find some kind of weights, multiply the criteria values by the weights, and then add up everything. Now to come to an overall criterion, which is then maybe called a score. Very simple idea, and actually it's so old that nobody knows where this idea originally comes from. It's in particular, it's for instance, very often used in the discipline of engineering. Then another also quite simple idea is called achievement levels or aspiration levels. This is based on some psychological ideas. People in psychology came up with some criticism to the simple weighting. People do not think in terms of weights, usually. It's very difficult for decision maker to come to meaningful weights. Instead, usually people think of particular values or levels they want to reach. And so a method was based on that, which is based on the idea people, decision makers, define aspiration levels. What do you want to reach for each particular criterion? And then we could say any alternative which fulfills those aspiration levels is a feasible one. Of course, often in situations, we would not come to a unique solutions when we do so. So this is also not so easy or clear how to use it in a very good manner, I guess. Another idea, which is a bit similar, is called reference point approaches or distance-based approaches. It's also based on the idea that the decision maker somehow specifies values in the objective space which he or she wants to reach. Unlike in the case of aspiration levels, these are usually values which are not possible to fulfill. Usually they are called ideal solutions, something which is not really reachable, but what would be the best thing someone would expect. And then if you have defined something like that, an ideal solution, then you could just say, well, let's look at all solutions and let's find those which are closest to the ideal solution. So we want to minimize the distance to such an ideal solution. There are a number of variants of such approaches. For instance, you could use different types of distance measures. You could combine it with weighting as well. Or you could also do just the opposite thing, not minimize the distance to a best solution, but maximize the distance to a most unwanted solution. That's also possible. Then one other idea which exists in that area is called utility-based approaches. Utility theory is a very old idea in economics, and people came up with saying, well, we always have a utility for everything we think of. The question is, of course, how can a utility function be determined? And usually the methods are based on the idea first that the utility function is somehow split into different criterion-specific utility functions. So for each criterion, a specific utility function exists. which somehow needs to be combined in some way, for instance, in an additive way. And then, of course, we need to define or determine each utility function. There exist specific methods how this can be done in a practical way. And then one other family of approaches is called outranking methods. This is a type of approach which has been much investigated in France and Belgium. Therefore, it's sometimes called also French School of MCDM. It's based on the idea that we somehow compare alternatives pairwisely and then define something what is called outranking graph or outranking relation from that, where we see each relationship between the alternatives. And when we have done so, we somehow evaluate this outranking graph to find the best solution. These methods are a bit complicated, but they have some advantages also compared to the less complicated methods, because you can also see, for instance, in a better way when alternatives are not well comparable. And finally, I would like to say something about visual and interactive approaches. The idea of using interactivity in MCDM is also quite old, coming from the early 70s. And here you see some example how this can be done in a practical application in the field of medicine. It's an example from radiotherapy for cancer. Usually when medical doctors treat cancer, they see something like this. So this could be a tumor, and here are organs. And then if you use radiation, you need to define how many radiation, how intensive radiation comes from which direction, because you want to hit the tumor, but you don't want to hit very much the necessary organs. And so you have also several objectives to be considered, which can be shown, for instance, in something like what is called a spider web interface, and then a medical doctor could just navigate in that, so not specify weights. The lung is more important than the spine or something like that, which is very difficult in medical terms, but somehow navigate around and find something like a good compromise. Okay, this is just some very brief overview of MCDM method. Let me now say something about the roots of this discipline. So I mentioned already that utilities theory is somehow important for some of the methods, and that goes back to the 18th century, developed by economists like those, including Vilfredo Pareto, who has first formulated something like the Pareto criterion in 1896. And then there was a lot of mathematical predecessors, people who dealt with handling order relationships or concepts in approximation theory from the late 19th and early 20th century. Then another origin is game theory, which was developed by mathematicians like Borel, von Neumann, Morgenstern, Nash, Blackwell, and others during the 20th century, from 1920 about until the 1950s. Then what is closer to our current understanding of multi-criteria decision-making are the origins in operations research, developed by, for instance, by Koopmans, Kuhn and Tucker, Slater, and others, so also in the 1950s and 1960s. And then there are many heuristic approaches, like simple additive weighting, which I've mentioned, where we don't know exactly where it comes from. It's so easy that there is probably not a single origin of that. Okay, then the discipline matured in the 1970s. In 1972, there was a first conference on multi-criteria decision-making that went on. Later on, that became an international conference, which was institutionalized and organized every year or every second year. Some working groups have been built, for instance, this one in France and this one in Europe. And a society has been founded, the International Society on Multi-Criteria Decision Making, in the 1970s. And the first textbooks appeared during the 1970s and 1980s. Also, a little bit later, an international journal has been founded. Okay, now some data about the internationality of that discipline. I've got, I had a look in the directory of the International Society on Multi-Criteria Decision Making, and there we can find that members come from 94 countries, which is really quite many. I've got here some statistical data of the different countries, and you see, well, also some, let's say, smaller countries and also developing countries are somehow represented in that society, but of course with a different number of participants. Here you see, well, for instance, among up to Iceland, the largest country is Finland. I don't know exactly why this is the case, but also, of course, other countries like not very unexpected France or Germany are quite strong, and also Canada. But I guess the largest country with respect to members in the society are still the USA. And then I looked at from which disciplines do the people come from. Now, I just looked into the directory and looked at the affiliation. Which department do they come from, or which faculty? Unfortunately, in many cases, about 50%, it's not easy to say, because the people specify their private address, or they just say university, so and so, but not which department or faculty they come from. So it's not easy then to find that out without further investigation. But you see, from those where we can find information about that, the largest area is mathematics and statistics, not very surprisingly, because a lot of the origins do come from that field. Then also economics, management, and business, all put into one category here is quite large. And then the engineering disciplines are quite large. And sometimes the people just say they come from operations research or decision sciences or optimization, which is a little bit a sub-area of those others. So often, if you look at the Department of Operations Research, this can be at an engineering school, it can be at a business school, it can be at a school of computer science, or even somewhere else at the mathematics department as well. So in that case, it can be in one of these other disciplines like mathematics, economics, or engineering, or informatics, or computer science, for instance. But you see also from some, let's say, areas where this is not so expected, people come like from geography or education or medicine or political sciences. So in a lot of areas, this can be used and is used. Okay, now I would like to very briefly discuss how do people work with multi-criteria problems and with the respective methods. I mentioned already some of the methods are quite easy to use by everyone, like simple additive weighting. Others are quite complicated and need a lot of understanding and further investigation possibly. So the typical scenario of solving a multi-criteria problem is that we do have a decision maker or a group of decision makers. They have a problem, a multi-criteria problem, and they have a lot of understanding of this problem. So they are usually experts of the application domain. That can be in business, that can be in engineering, or anywhere else. And on the other hand, as the methods are often quite complicated, we need someone who is usually called a decision analyst, who has a good understanding of the methods, who knows what information is needed, how the methods work, what to do with the results of the methods, and other things. But of course, it's not just enough to have the two of them. They need to communicate. No? So they need somehow to inform the decision analyst about the problem. The decision analyst needs to understand it. No? So he cannot just say, give me a table of data and then I do it, and then you get the result and then it's finished. Now, it's usually a consulting process, and it needs a lot of communication from both parties, and therefore I wrote here as well, the decision analyst should have a good understanding, and he or she needs to hear and understand what the decision maker says and wants, and he also then needs to somehow explain the result, and probably it's not just a finished result, it needs further discussion and maybe further investigation as well. Okay, let me come to the last slide, a little bit about current and future trends in multi-criteria decision making. So first of all, I mention here treating more real-life multi-criteria problems. When we look back 30 years, there was a lot of investigation in theory and methods, but not so many convincing practical applications. This has changed over the last 30 or 40 years. So today, very many problems are solved for many different areas, and I assume that this trend will go on. And in particular, people try to solve more complex problems. One area where we find quite complex problems is the field of combinatorial optimization, where often these multi-criteria approaches are combined with other powerful methods which are able to solve combinatorial optimization problems, for instance, methods from the field of meta-heuristics or evolutionary computation. Then another interesting area is how do the minds of people work? What kind of psychological basis do these methods have? Can we use results from psychology or cognitive theory to somehow better, to give those methods a better fundament? No? So this is, I guess, also something which is still not sufficiently worked out. And finally, the software side is quite important. I showed you this interface where medical doctors can plan a radiotherapy for a tumor. This is certainly something which should go on. People, if they want to work with that, they should have a user-friendly software, which is not a general software, but which is somehow adapted to their specific needs and the problems to be treated, like, for instance, in radiotherapy. And finally, that also means it would be nice to have respective methods integrated with other software solutions, like, for instance, general business software. Usually, this is missing. If you look at ERP software, for instance, they do not have any support for multi-criteria decision making. Maybe they support something very easy like weighting or so, but usually they don't provide further means of treating problems like that. Okay, that's all I wanted to tell you.